Behind every high-level script you write, all of your data eventually collapses down into raw zeros and ones. We are going to look at exactly how Python translates your script into physical memory, and why ignoring this translation causes developers to accidentally overwrite their own variables. Let's open the IDE and set up our active workspace to run some diagnostics. Look at this split-screen comparison. On the left is a broken script throwing constant overwriting errors, and on the right is a clean, functioning memory architecture. The difference here is strictly how the data is stored physically. Tracking this hidden layer is how we identify why data changes in one part of a program when we only intended to modify another. Step 1 is establishing the bottom layer. To declare a raw binary variable in Python, you write a lowercase b directly before a string of characters. When we execute this basic assignment, the terminal returns the exact byte representation, confirming the data type. A byte storage container opens and fills up sequentially with the exact binary digits of our input code. This rigid container represents the lowest level of data interaction. Every abstract layer of logic stacks directly on top of this physical foundation. Verifying this bedrock layer ensures our memory allocation is strictly defined before introducing complex data structures to the application. Let's move up to standard text. We'll create a string assignment in the environment, setting a variable to the word Python. This introduces the principle of immutability. Once a basic data object is logged into memory, the system locks it. You cannot alter its existing state. Look at this panel. If a developer attempts to isolate a localized character in the string and change it, Python throws a type error. To enact a change, you have to execute a complete workaround, destroying the original variable entirely and recreating a new one in a fresh memory slot. By locking the text down, Python guarantees that complex logic won't inadvertently corrupt your stored data. It serves as a core security feature. We switch over to list creation now. We assign a sequential array of integers, 1, 2, and 3, to a primary variable, a. Next, we assign a secondary variable, b, to equal variable a. We then execute an append command to add the number 4 strictly to the b variable. We print variable a to check our work. The terminal output reveals that the number 4 is there too. Variable a was permanently altered. This diagram reveals the structural reality of that error. We have 2 separate nodes floating in our environment. Instead of a fresh list for b, it created a memory pointer. Both variables target the exact same physical location. When the append operation drops the number 4 into that central box, variable a instantly reflects the change because it's looking at the exact same data source. The equals operator in Python lists creates a direct memory reference, dictating how data flows through your entire application. Let's shift this from abstract integers to a practical array containing specific user profiles for a database. We replicate the shared reference operation, assigning a new team variable directly to our foundational users list. Then we execute a command adding a third distinct user profile exclusively to the team variable. Look at this interface. The moment the code executes on the left, you see the immediate synchronization effect on the live user dashboard on the right. All 3 users update simultaneously. This automatic synchronization is highly efficient for real-time updates. But if you needed to keep the original user list pristine as a backup, that shared reference just created a massive operational risk. Unmanaged memory references are how developers unintentionally overwrite production data, turning a simple update into a permanent loss of the original records. This diagram highlights the exact beginner assumption you need to avoid, assuming the equal sign duplicates your data. Immutable data locks security in place, while mutable lists prioritize shared memory routing. By tracking all of these terminal outputs, you've successfully verified the exact physical architecture Python uses to allocate memory. The necessary next step for safe manipulation is building a true copy method, allowing us to safely alter a list without touching the original database. Visualizing how memory links operate ensures your data stays exactly where you put it, even as the logic of your application